Hi there, and welcome to day number 21 of Unit 1. We are working our way through Chapter 3. We're talking about two more application concepts today. We're going to talk about motion on a ramp, and we're going to talk about relative motion. You should watch one of our class videos if you didn't already to get the ranking test day 21. But this is meant to be the flipped version of the class. So if you're good with this, then you're good overall. And this is these two lessons today I think are very manageable. But by the end of the day today, we have our key takeaways. And again, these are the things that if you can say them without lying, you're good to go. I can determine the acceleration of an object on an incline. That's given by this formula right over here. And I can explain the concept of relative motion and how it applies to relative objects. No really new strategy bank today. We are going to still be using kinematics as a mathematical strategy, but nothing new or anything today. So let's go ahead and get into it. Motion on a ramp. So let me draw a picture for you. I do this demonstration in class, but let's say I have a cart and it's going down the ramp. And that cart has some acceleration. We'll call that AX. And we'll just call going down the ramp the positive X direction, even though it's on an angle. Now, let's say that this is right here is a book. Now, if I change this to 3 books, and I have the same ramp, with the cart going down it, there's also an acceleration x. And let's call this acceleration x2 and acceleration x1. And what can I say about ax2 versus ax1? Well, it should be really obvious that ax2 is going to be greater than ax1. So now let's say I go up to 5 books. So we'll say ax3 is 5 books versus ax2. Well, it's going to be the 5-book one is going to be greater. And acceleration is just going to get greater and greater and greater. And my question to you is, at what point does acceleration stop getting greater? And some of you might think of this as, well, if the ramp is straight up and down, that is the fastest or the greatest angle that I can have an incline is straight up and down. So my acceleration in the x direction at that point, well, that's free fall acceleration. So anything less than this vertical 90 degrees has to be less than g. So let's get into motion on a ramp and try to see exactly how we can derive this. You don't have to be able to derive this. All you have to know is that ax equals g sine theta, all right? If that's all you get out of this, anytime we got a ramp, that's all you need. But you're in AP Physics, so we're going to talk about where it comes from. Just like in biology, they talk about where babies come from. So I did the demo, or I just talked through the demo, cart on the track. If I were to graph my graphs, all my position versus time graphs are going to be exponential. All my velocity versus time graphs are going to be linear. And all my acceleration versus time graphs are going to be horizontal. But when I start to increase the ramp itself, they'll be exponential faster. There'll be better slope, or a greater slope velocity. It'll be a higher acceleration. So as I go from trial to trial, things are just going to happen at a greater rate because they all have greater accelerations from trial 1 to trial 2 to trial 3 as I'm increasing the angle of the incline. So accelerated motion on a ramp. A cart or a crate will slide down the ramp, and we'll call it a frictionless ramp because we haven't learned about friction yet. We're going to talk about that in the next unit. The crate is considered to accelerate parallel to the surface. So the surface runs at whatever this angle is. The crate also runs at whatever that angle is. So what we do is we call this the positive x direction to make that easier. But that both the acceleration and the velocity vectors are going to be parallel to the ramp. So if we look at, we've just been talking about vectors and breaking things into components. If we look at acceleration, free fall acceleration is straight down. There is an since we're going to choose our ramp to be going down in the positive x direction, our acceleration is not free fall, but it is the x component of free fall, and this is the y component. The y component simply pulls the block into the ramp, okay? Next unit, we're going to talk about how it pulls it into the ramp, and then the ramp pushes it back up, and that's called the normal force, and this is called weight. So next unit, when we talk about forces, we'll address this concept again. We don't need to worry about it right now. But if the ramp is at some angle theta, due to some geometry stuff, you guys are probably better at proofs than I am at this point. I think it has something to do with alternate interiors or congruent, but in any case, these two angles are the same angle. So if I care about the x component of that angle, that's the opposite, and hypotenuse is free fall. So opposite, so I got sine of theta equals the opposite, which is ax, over the hypotenuse, which is g. So ax equals g sine theta. And I put a plus or minus here. Why is there a plus or minus there? Well, if this is the positive x direction and it's going down the ramp, that is a positive acceleration. However, if the positive x direction is going down the ramp and I push it up the ramp, guess what? We're going negative acceleration, okay? So it depends on how you define your axes. Actually, if I push it up the ramp, I'm slowing down in the negative direction, so it's still positive acceleration. And that makes sense because it shouldn't change. But if we change directions, then we do have the opportunity of having a negative acceleration. But for the most part, we're just going to call down the incline the positive direction, so we don't have to worry about having a negative acceleration. But it can, if you set up your problem, it can absolutely be a negative acceleration. Awesome. So, I screwed up here. Ball, I gave you the answer. Ball rolls up the ramp and then back down. So it goes up the ramp, and we're calling this the positive x direction. Whoop, I am writing with blue on blue. That's a terrible choice. I just love the color blue. So that's the positive x direction, but it's slowing down in the positive x direction. So we're going to have negative acceleration. And then it's going to speed up as it goes back down the ramp. So it's speeding up in the negative direction. That is also negative acceleration. So we have a flat line. Now at the top, at the tippy top, my velocity for 1 instantaneous second is 0. But my acceleration never stops. The gravity doesn't go away. We're going to talk next unit. Forces cause acceleration. The force of gravity doesn't disappear. So the magnitude of where this should be g sine theta. Depends on the angle of the ramp and what planet you're on. Now, so that's why you got to be careful with one like this, because it is slowing down and then speeding up, but it's slowing down in the negative direction, and it's slowing down in the positive direction and speeding up in the negative direction. So this is not okay. That's not the right graph. All right, awesome. Here's an example problem. The Willamette Ski Pass area in Oregon was the site of the '93 National Speed Skiing Competition. The skiers started from rest and then accelerated down a stretch of the mountain with a reasonably constant slope. Now that's important because otherwise we can't set up a good triangle. Aiming for the highest speed possible when at the end of the run. During the acceleration phase, the skiers traveled 360 meters while dropping a vertical distance of 170 meters. What is the fastest speed a skier could achieve at the end of this run? Now, I will tell you that this is a theoretical maximum, and it won't actually play out that way. Why? Because there's friction, and you're not just accelerating on a frictionless track. So, just a heads up with that. But let's think about this then. There's very little information. There's absolutely no information here except about the physical mountain itself. So let's, instead of drawing a mountain, let's pretend that is just a triangle. Why? because triangles are way easier to draw than mountains, even though mine's still bad. And here's a right angle right here, okay? So think of your skier going down this triangle. He may look like a snowboarder because it's in 2 dimensions. And they traveled 360 meters while dropping 170 meters. So if I have the incline of that angle, I can determine the acceleration. And indeed, I have the opposite and I have the hypotenuse. So I can go ahead and I can say that let's find the angle by using sine. So sine of theta equals the opposite, which is 170 meters, divided by the hypotenuse, which is 360 meters. And I can go ahead and take the inverse of both sides. So theta is the sine inverse of 170 meters over 360 meters. I don't know if you ever realize this, but if I take the sine inverse of something, like they're both meters, for example, in this case, my meters cancel. So that's why sine has no unit. And that has to make sense. But we'll talk about this later on, next unit. If I have like, never mind. I'm not going to talk about it right now. Never mind. But if I have, I'm going to talk about it anyway. If I have different units, I can't use the angle because they're not the same unit. The units don't cancel. But anyway, I get theta equals 28 degrees. And that makes sense, right? Because if they're skiing, it can't be more than 32 degrees because then the snow would melt. A little flash joke for you there. All right, so now I have some information. So now let's get to the kinematic side of this. The first thing I know is that acceleration is g sine theta. So that's 9.8 meters per second squared. This is positive because we're going to call this the positive x direction. 9.8 meters per second squared times the sine of 28 degrees. So go back to my calculator, 9.8 sine 28. I get 4.6 meters per second squared. So it didn't tell me my rate of acceleration. However, since I understand the concepts of acceleration on a ramp, I can solve for my magnitude of acceleration, and it is 4.6 meters per second squared. Now, if he's starting right here, or she, my initial velocity, I can assume, is 0 meters per second. I also know the length of the ramp, or the length that they ski, is 360 meters. So delta x is 360 meters. Or I could say xi is 0, xf is 360 meters. Though that's also okay. And finally, I know, or I'm looking for my final velocity is my question mark. So now this is just a kinematic, right? It's a kinematic equation. I have VI, I am looking for VF, I have A, I have delta X, okay? So I can't use VF equals VI plus a delta T because I don't have the time interval. But if you look through your kinematic equations, you should find, hey, why not use VF squared equals VI squared plus 2A delta X? I can go ahead and save myself the problem of the VI squared because that is in fact 0. And I get VF equals the square root of 2A delta X. And I go ahead and plug in. Oh my God, I'm so close to running out of room. 2 times 4.6 meters per second squared times delta X of 360 meters. And again, this is a theoretical maximum, not including friction. So I expect this number to be higher than potentially a reasonable value. So 2 times 4.6 times 360, and I'm taking the square root of that. I have, all right, ready for this one? 57.5 meters per second. Now, if I go ahead and go to the Google machine and put 57.5 meters per second to miles per hour, it's roughly 128 miles an hour. Snow does not allow you to accelerate without friction, okay? You're never going to get that. This is a theoretical high speed. So it's a little unreasonable. But if you ever watch, like, what is it, the Solemn or whatever, those guys are freaking crazy, and they're going very, very, very fast. So they do actually get very fast in the downhill. And you're thinking about dropping 170 meters, which is a very tall hill, over only the course of a distance of 360 meters. So it is a relatively high acceleration. All right, awesome job with that problem. So here it is again. Okay, another partner example problem. So a problem for you to try is that a new ski area has opened, emphasizes the extreme nature of skiing possible on its slopes. Suppose an ad intones free fall skydiving is the greatest rush you can experience, but will take you as close as you can to get on land. When you tip your skis down the steepest runs, you can accelerate it up to 75% of the acceleration in free fall. What angle should give you such an acceleration? Now, I got a cool little trick for this problem. So we know that AX equals G sine theta. Now, a lot of you will probably say, all right, well, the acceleration is 0.75 G. So let's go ahead and figure out what that is. And you go to your calculator and you say 0.75 times 9.8, and then you get 7.35, and you try to carry out this problem. But here, watch this. If it's 0.75 G equals G sine theta, all you mathematicians know that my g's cancel, and it's just 0.75 equals the sine of theta. How easy is this problem? So then theta is going to equal the sine inverse of 0.75. So the sine inverse of 0.75, I get 48.6 degrees. Okay, now that's pretty much like a 45 degree, that's pretty much like a 45 degree angle. It's barely more than that, but look at how much, we're at 75% of G, and 45, you think of it as like a half, right? But it works like a sine function, not a linear function. So as I increase the angle, I do not linearly increase the acceleration. Don't assume that, because that is not correct. All right, the other side that we have to talk about today is relative motion. And this is just kind of like a frame of reference concept. So we're going to jump right in with a picture. So here I have four things. I have Bill on his bike, the runner at 5 meters per second. Amy looks like she is pissed at Carlos, like Carlos just kicked her out of the car and is driving away. But relative motion just refers to how fast an object moves relative to another object. So in the picture below, the runner moves at a different velocity relative to each of the objects. So let's take a look at that. So the runner relative to Amy is 5 meters per second. That's a stationary object. That makes sense, right? So they're running at 5 meters per second. And any time, or most of the time that we solve physics problems, we're relative to a stationary observer. However, and Carlos is 15 meters per second relative to Amy. However, Bill and the runner are both going at 5 meters per second. So relative to each other, they're not moving because they're both moving at the same speed. Okay, so it's kind of like when you're driving next to someone on the freeway, they look like they're standing still if they're driving the same speed as you, because you guys are moving together. You're moving as at the same velocity. So your relative velocity is 0. Now, Carlos, compared to Bill, Carlos is going 15, Bill's going 5. Carlos is passing Bill at 10 meters per second, right? He's going 10 meters per second faster than Bill. So if he's passing Bill, Bill's going to see him, but he's going to perceive him as only passing at 10 meters per second. So it's the difference of the two velocities. Now, conversely, if a guy is walking this way to the left at 5 meters per second, or running at 5 meters per second, Carlos is going to see him coming at 20 meters per second, right? Because he's going 15, the guy's coming at 5. He's going to see that happening at 20 meters per second. So it's just a concept of how velocities are relative to one another, how they compare to one another when an object when objects are in motion. Okay, it's just a frame of reference. We're not really doing anything with this. It's just kind of getting you to think about it. It's an application of kinematics. So here's an example problem. This is more of a vector problem, but we have a skydiver jumps out of an airplane 1,000 meters directly above his ideal landing spot. He quickly reaches a steady speed going at 35 meters per second. So he is going at 35 meters per second down, and there's a breeze going to the west at 7 meters per second. So the question is, what angle does he fall with respect to the vertical? So that's going to be this angle right here, and this is, of course, a right angle. And when he lands, how far is he from his desired landing spot? Well, let's get to that in just a second. The first thing is we're going to use, to find the angle, it's opposite and adjacent. So theta is the tan inverse of 7 meters per second over 35 meters per second. And again, my meters per seconds cancel out, as I mentioned earlier. So I have the tan inverse of 7 over 35. I get theta as being 11.3 degrees. Okay, so that's 11.3 degrees. When he lands, how far will he be from the landing spot? Well, he did drop straight down on it, but the wind is pushing him 7 meters per second to the left. So his velocity in the x direction is 7 meters per second. And we're curious about the displacement in the x direction. So what I need is the time in the air. And the time in the air is going to come from the y direction. And this is actually a good concept to link us to our next big topic, which is projectile motion. Because sometimes we can use information in the y direction to help us in the x direction, because he doesn't spend more time in the x direction than he does in the y direction. But his velocity, let me change colors here, keep this straight for you. Velocity in the y direction is 35 meters per second. His displacement in the y direction is 1,000 meters. And you might be saying, isn't he accelerating as he goes down? He quickly reaches a steady speed. So when you skydive, you reach what's known as a terminal velocity, meaning that you're not going any faster. You're going as fast as you're going to go because of air resistance. We'll talk about that a little bit in the next unit. And now let's solve for time. So running out of room again, but Vy, delta y, and delta t. But we're going to treat this as uniform motion. So delta y is Vy delta t, which means that delta t is delta y over Vy, which is 1,000 meters over 35 meters per second. So 1,000 divided by 35, I get a delta t of 28.6 seconds. Let's go ahead and plug that in right here, and then let's solve the other problem. So delta x is Vx delta t, which is 7 meters per second times 28.6 seconds that I got from the y. 7 times 28.6. He's going to land approximately 200.2 meters from where he should have fallen. All right. So just a quick little example problem, actually using uniform motion twice. And the concept of vectors, because both things can be happening at the same time, right? We got an x direction and a y direction. And so here it is a little bit neater. Anyway, we're going to be dealing more with this concept of moving in the x and the y direction in our next section when we get into our final big application in this unit, which many of you will hate, even though it's not anything harder than what we've been doing, and that is projectile motion. And we'll be taking a look at that in the next segment.